Hi everyone. In today's video, we're going to use two graph neural network libraries. The first one is pytorch-geometric and the second one is Jraph. We will code Graph Convolutional Network, GCN, in both libraries and see how things will work out for us. So let's jump right in. So I got my notes here just to understand how these libraries are used. Deep learning libraries, we got PyTorch and JAX. But JAX is not a standalone deep learning library. It needs either Haiku or Flax to work. There is another deep learning library, as you know, it's called TensorFlow, but I'm not aware of any graph library that uses TensorFlow. The graph needs special data structures to work on it. It got edges list, it got the adjacency matrix, the feature matrix, and the labels. So it needs its own data structure. As the research advances in graph neural network, there was an urge to create a graph neural network library. So we ended up with a pytorch-geometric that uses PyTorch as a backbone and Jraph that uses JAX as a backbone. So in this video, we're going to test both libraries and to see the similarities and differences between these two libraries. So here's the GitHub page for pytorch-geometric, PyG. pytorch-geometric is developed by PyG team, as you can see here from the GitHub repository. So PyG pytorch-geometric is a library built upon PyTorch to easily write and train graph neural networks, GNNs, for a wide range of applications related to structured data. The thing is that pytorch-geometric got way more tutorials and way more implementations than Jraph. I don't know, maybe this is due to, because pytorch-geometric was developed before Jraph. I'm not sure. Or pytorch-geometric is adopted by so many teams. I don't know, but the tutorials that you will find in pytorch-geometric are so many. And this is the GitHub page for Jraph. It is developed by Google DeepMind. So Jraph is designed to provide utilities for working with the graphs in JAX, but doesn't prescribe a way to write or develop graph neural networks. So they only provide these three Python files. Graph.py, which provides a lightweight data structure, which is a graphs tuple. You can package the graph in a graphs tuple variable, and you can use it in Jraph. Utilities for batching dataset and for supporting JIT, just-in-time compilation for JAX, and utilities for defining losses and partition of the inputs. And the final thing, they provided models.py, which has the models, the GCN model, the graph attention model, but they said they do not manage parameters for you. For that, consider using Haiku or Flax. See the examples for more details. So in addition to JAX, you need Haiku or Flax to manage the parameter. So in this table, I find some differences between pytorch-geometric and Jraph in defining and packaging the graph data for processing in a GNN. So for a graph, pytorch-geometric uses data variable, which is similar to Python dictionary. But Jraph packages the graph in a graphs tuple variable, which is similar to Python tuple. And for the feature matrix, pytorch-geometric uses torch tensors, which is understandable because it uses PyTorch as backbone. But the type of this tensor, of the data in this tensor, are of torch float32. But in Jraph, it uses JAX NumPy, which is an extension of NumPy that works on JAX. It's optimized for parallelization on the GPUs. It uses a NumPy in the array, but the type's a float32. This is the native float32 in Python. It doesn't use the torch float32. It uses a native Python. And for the edges list, what PyTorch is doing is it uses 2 by E torch tensor. E is the number of edges. So if we have 100 edges, the torch tensor will be of size 2 by 100. 2 rows and 100 columns. In the first dimension, the edges index 0 is the source, the node that sends the edge. And on the second dimension is the destination node, the node that received the edge. The data type in this torch tensor is torch.int64, which is understandable because then the index for each node is an integer. They're not allowed to have a decimal point, so it's understandable to have it as an integer. What's interesting is that Jraph defines the edges list in 2 separate arrays. Both arrays are JAX.NumPy in the array. The first array is the senders, which nodes that send the edge. And in the second array are the receivers. I think there are 2 main differences between JAX and pytorch-geometric. The first one is the data type they use to define the graph. pytorch-geometric uses data variable, and Jraph uses graphs tuple for the graph. And the second difference is how the way they define the edges list. PyTorch-geometric uses one torch tensor to define the edges index with 2 dimensions, 1 dimension for the source nodes and the second dimension for the destination nodes. But in Jraph, it separates this process. It puts the senders in one jax.numpy ND array and puts the receivers on another jax.numpy ND array. So here's the code that I'll be using to implement GCN on pytorch-geometric and Jraph. By the way, you can find a link to this notebook in the description below. I got a disclaimer in red, so it must be important. It's about not getting the consistent result for the test set. I'll talk about that at the end of the video. It's in the last cell. So first, an acknowledgement. I borrowed some code from pytorch-geometric tutorials and some code from interactive Jraph collabs. These tutorials are in the GitHub pages of pytorch-geometric and Jraph, and these are the references for pytorch-geometric and Jraph. So here's the plan. I'm going to load Karate dataset from pytorch-geometric, and I'm going to load CORA dataset from pytorch-geometric. Because Jraph does not include datasets, I'm importing these libraries from pytorch-geometric. Then I'm converting these libraries to be compatible with Jraph, just to make sure that I'm using the same train index. I'm training with the same samples, not other samples. So I'm training pytorch-geometric and Jraph on the same training mask. This is the most important thing. So here I'm importing Karate Club dataset from pytorch-geometric. You can find more about this dataset on this link. I'm storing the number of features and the number of classes, and I'm getting the first graph in a variable I call data Karate Club. And here I checked the data type for the feature matrix. It's torch float 32, and for the edges list, it's torch and 64, and for the labels matrix, it's torch and 64. Then I'm defining a GCN class with 2 GCN conv layers. The first one maps the number of features to the hidden channels. I'm defining the hidden channels to be 16. And the second convolutional layer maps the hidden channels to the number of classes. So I set the optimizer to Adam, and the criterion is the cross entropy loss. These are 2 functions for training and testing. And training, I'm passing the data and the mask, which usually is the training mask. For this test, the model is set to evaluation, and the predictions, I'm getting the predictions from the model. And because the predictions are retained as probabilities, I'm just getting I'm running argmax on the first dimension just to get the maximum probability, which is the maximum class. And I'm comparing that with the ground truth to compute the accuracy. So it converges after 30 epochs to 1. Now in this section, I'm making Karate Club dataset compatible with Jraph. So I'm defining a Jraph graphs tuple. You can see here GNP stands for jax.numpy, jax.numpy, which I import at the top as GNP. And I'm getting the first dimension from the edges index as the senders, and I'm storing that as an ND array. I use a squeeze just to remove the first dimension. So for example, in Karate dataset, it will retain 1 by 156, and I don't need the first dimension, which is 1. So I'm using squeeze just to keep the 156. And I'm checking the data types. So the data types for the data type for the feature matrix is float 32, and the data type for the senders is integer 32, and for the receivers it's integer 32, and for the labels it's integer 32. Here's how we define a Graph Convolutional Network in Jraph. So the input is a graphs tuple, and it will return a graphs tuple. The first layer, I'm mapping linearly the graph into the number of features, which is in our case is 34. HK here stands for haiku. So the linear layer from haiku. Then I'm mapping the number of features to the hidden dimension, which is I set to 16 using a haiku linear function. And after that, I'm applying ReLU to that. This part here is equivalent to the forward function in pytorch-geometric here, which is mapping the input features to the hidden dimensions. In our case, it's 16, then applying ReLU. At the end, we are mapping the hidden dimensions into the number of classes using the haiku linear function. And this is the optimized graph function, which contains the training loop or the Jraph GCN class. So when we pass the network here and the number of steps, we are expecting in return a GNP array. So the labels will be the graph labels, which we defined earlier, and the parameters are the network initialized to a random seed. And before each one of these functions, we are using just in time, or JAX, and these functions will be executed later. So we'll jump here to the for loop. If a step is multiple of 10, we will print by calling the accuracy for the parameters and the train mask. So we're calling this function. I'm commenting out the JIT part here because I'm getting an error when I index the nodes using the mask. So I think it doesn't allow masking while applying the JIT. So I'm commenting it out. So by passing the parameters and the mask, I'm getting a decoded graph. Decoded graph, basically I'm applying the network using the parameters and the graph. And then I'm getting the correct labels by counting how many of the graph nodes actually equals the ground truth. I'm dividing the correct predictions over all predictions, and I'm returning the accuracy, and I'm printing the accuracy here at the first step, the training accuracy. Then after printing this statement, I'm updating the graph by calling the function update, this function here, and I'm passing the parameters. So I'm computing the gradient using jax.grad for the prediction loss. The prediction loss is this function here. I'm passing the parameters and computing the decoded graph. I'm getting the logits for the training mask, and I'm performing one hot label for the number of classes, and I'm computing the cross entropy between the logits and the ground truth labels. So this will return the loss to the update function. It will compute the gradient and update the parameters, and the new parameters for this epoch will be retained here. Then again with the next epoch, printing the accuracy and updating the graph. So here it converges after 20 epochs. So for Karate Club dataset, both of our GCN implementations, the one on pytorch-geometric and the one in Jraph, got 100% on the training dataset. So let's load another dataset, which is CORA dataset, and see how things will go. So I'm loading the dataset from pytorch-geometric. So I'm calling the GCN implementation on pytorch-geometric for this dataset, and it converges after 80 epochs. Then I'm converting CORA dataset to make it compatible with Jraph. Then I'm defining a new network for the GCN implementation on Jraph, and I'm calling the optimizer graph that brings the train accuracy and updates the graph. It converges after 20 epochs. For both Karate Club dataset and CORA dataset, we got 100% accuracy for the training, which means both GCN implementations, the one in PyTorch and the one in Jraph, knows how to classify the training dataset. Now to the big disclaimer, the one that I'm setting at the top of this notebook. And please don't use this code in production because I'm not getting consistent results on the test dataset. So when I use the test mask for PyTorch test function, I'm getting a 0.78, 78%. But when I'm using the test mask on the decoded graph using Jraph, I'm getting only 72. I don't know what is happening because both implementation knows how to classify the training dataset. It should be the same for the test dataset because they already defined the decision boundary between these classes. I don't know what's happening at the inference time, and I have to figure this out. But for the time being, this notebook is solely designed for educational purposes. So my final remarks on pytorch-geometric and Jraph. Both libraries were built on very well-known deep learning libraries. So pytorch-geometric was built upon PyTorch, and Jraph was built upon JAX. But there are some differences. They're not the same. So JAX is just intermediate. It needs flags or haiku for higher level functionality. But in PyTorch is standalone. I'm not showing which library is better for Graphneuralnetwork. I'm just showing the functionality of both libraries, how they are packaging the graph information, how they are dealing with data types. So I hope this notebook will be very helpful for the people who are planning to make the transition. And let's be honest, sometimes it's not you who decide the transition. If you are trying to replicate the results from a paper that uses Jraph, then you have to use Jraph. If you are part of a team that uses pytorch-geometric, then you have to use pytorch-geometric. So it's better to know both libraries just to make the transition if you have to. But if you are comfortable with any of these libraries, then you're okay. That's it for today's video. If you find this video helpful, please like and subscribe. By the way, you can find a link to the notebook I'm working on in the description below. Thanks for watching. Bye.